Hi and welcome to Unit 1, Topic 3, Video 2, and in this video we're going to be talking about direct proof. So, direct proof is one of our four types of proof we're looking at in this topic, and a direct proof is where we develop a chain of logical statements that generate a proof. So I've got an example here that is totally not mathematical, but let's imagine that I make the statement that I am taller than my grandmother. Now, I may have no proof of that. Unless you see me standing next to my grandmother, you have no proof of that. Maybe I could state some numbers. Say, well, I'm 175 centimetres tall and she's only 165 centimetres tall. That would be a good proof. And as long as it's true, then we're all good to go forward. But here's another way we could look at it that is a direct proof via a middle point or a middle fact. Okay? So my claim is that my height is greater than my grandmother's height. And so this is RTP, which means required to prove. You don't need to say RTP, but you'll see that pop up in some proofs. Now, I'm going to make the statement that I also have some information about my uncle's height. So I'm calling that HU. Now, let's say my grandmother lives in the UK. So we can't compare directly. Maybe we can Zoom call, but we still can't compare those heights. But recently my uncle visited her. Then he visited me. And he claimed that he is taller than my grandmother. So his height is greater than my grandmother's height. And we know because we're currently talking that I am taller than him. So I am taller than him and he is taller than my grandmother, which implies that I am taller than my grandmother. And then we have this little QED, which I'll talk about in a minute. But here's a really good example of our implied statement that P implies Q, or in this case, that HM being greater than HU and HU being greater than HG implies that HM is greater than HG. It's worth pausing now and taking some time to think about that. QED is shorthand for quod erat demonstratum, which is Latin for that which was to be demonstrated. Or, as I like to say, I told you so, or so there, or bam. Anyway, so that's our first proof and a bit of understanding. Let's have a look at another one, which is a little bit more number-based. Prove that if a number is odd, then its square is also odd. Now, this comes with a really important caveat. So what we're going to say is, let's let a number be x. So we're just going to say x is a number. Now, we're dealing with numbers. It hasn't really said integers, which maybe I should have said in the question, but we're going to assume it's an integer. Obviously, if it's rational or even irrational, just a real number, we haven't really defined odd and even in that set. So we're just going to talk about integers. Now, what I really want to do is I want to prove that if x is odd, then x squared is odd. That's what I'm aiming to prove. And to do that, I need to have an understanding about what happens when x is odd. So here's something that's really important. Have a look at this number. If n is an integer, then 2n is even. And 2n minus 1 is odd. Take a second to think about that. Note here, we could also say 2n plus 1. Sometimes it works better if it's 2n plus 1, etc. But we can actually define our odds and evens by multiplying by 2 and then looking at those two sets of sequences. So 2n and 2n minus 1. And they define the evens and the odds. So what I'm going to say is I'm going to say, well, if x is even, x is equal to some number 2n minus 1, where n is an integer. So I didn't need to make that statement again, but I probably wouldn't say this in my proof. X equals 2n minus 1, which means that x squared is equal to 2n minus 1 squared. And we know how to square binomials, so we get 4n squared minus 4n plus 1. And you're welcome to go ahead and do that a bit slower if you want evidence that that works, but that's what we get when we square that binomial. And of course, 4n squared minus 4n plus 1, and here's another really important way to prove something. If we factorize the first two terms, we get 2 times 2n squared minus 2n. You might be thinking, why don't you take the extra 2 and the n out? Well, there's a very particular reason, plus 1. And this is equal to 2 times something plus 1, which we know is an odd number because 2 times something will definitely be even, plus 1 makes it definitely odd. So hence, by direct proof, we have proven that if x is even, then x squared is even. And we can finalize this by saying this is equal to 2m plus 1, where m exists, or m equals 2n squared minus 2n, which exists in the integers as well. And therefore, x squared is odd, and QED if you would like. Okay, so that's an example of direct proof, and we've got one more to do before we finish this video. Example 2, required to prove if x is greater than y and c is less than 0, then cx is less than cy, where x, y, and c are real numbers. So they're not integers anymore, they're real numbers. So this is an example of a trickier proof to demonstrate using elegance in mathematical proof, because you can really play around with it and it might not quite work out. But in terms of using elegance, there's some good ways of doing this. And I'll show you a couple of options which are nice. That should be option 1. So option 1 looks a bit like this. If x is greater than y, I don't want to muck around with the inequality too much, but I can subtract y from both sides to say, well, x minus y must be greater than 0. And then I can multiply by c, and I get c times x minus y is greater than 0, but because c is less than 0, it swaps the inequality. And then that gives me cx minus cy is less than 0, which gives me cx is less than cy when I add it back on. What this does is it fixes an element of the negative and positivity of x and y, because they could be different. X could be positive and y could be negative. And so it's nice to bring them to both sides. It would still work because option 2 looks a little bit like this. Option 2 is to say if x is greater than y and then we multiply everything by c, we get cx is less than cy, because we know that when we multiply by a negative, then we swap the inequality. But it would be considered a little bit more elegant to go this way just to avoid the negativity of x and y. But realistically, at your level, probably either or. So there's the end of video 2. I hope the direct proof makes sense. All the best.